Welcome back. For 13 episodes, a vector has been an arrow, or a list of numbers. Today we make the move that gives linear algebra its enormous power. We stop asking what a vector is made of, and ask only what we can do with it, add 2 of them, and scale 1 by a number. If those 2 operations satisfy 8 simple axioms, the collection is called a vector space, and every theorem we have proved for arrows in Rn instantly applies. The payoff is the cast of new examples. Polynomials turn out to be vectors, so do matrices of a fixed size, functions, and infinite sequences. None of them looks like an arrow, yet all obey the same rules. Then we look inside. A subspace is a vector space living within a larger one, and a single short test tells you whether a subset qualifies. We will see that spans are always subspaces, and that every space has a smallest and a largest subspace. Here is the complete definition. A vector space is a set V together with 2 operations, adding 2 elements and multiplying an element by a scalar that satisfy 8 axioms. 2 are closure axioms. Adding 2 vectors keeps you inside V, and scaling a vector keeps you inside V. Addition is commutative, so order does not matter, and associative, so grouping does not matter. There is a special zero vector that leaves any vector unchanged when added, and every vector has a negative that cancels it back to 0. Then the rules linking the 2 operations, scalar multiplication distributes over a sum of vectors, and also over a sum of scalars, multiplying by A, then by B, equals multiplying by A times B, and scaling by the number 1 changes nothing. That is the entire definition. Notice it never mentions arrows, components, or length. Any set with 2 operations obeying these 8 rules is a vector space, full stop. Let's meet the first non-arrow example, polynomials. Fix a degree bound n and let Pn be the set of all polynomials of degree at most n, things like a constant, plus a coefficient times x, plus a coefficient times x squared, on up to x to the n. Can we add 2 such polynomials? Yes, just add the matching coefficients and the result still has degree at most n. Can we scale one by a number? Yes, multiply every coefficient, and again the degree is unchanged, so the set is closed under both operations. The zero vector is the polynomial that is just 0 everywhere. Check the rest of the axioms and they all hold, because adding coefficients behaves exactly like adding tuples. In fact, a degree n polynomial is secretly a list of n plus 1 coefficients, so Pn behaves just like R to the n plus 1. It is a genuine vector space, and there is not an arrow anywhere in it. 3 more examples, each stranger than the last, all vector spaces. First, matrices. Fix a shape, say n rows by n columns, and take all matrices of that shape. You add them entry by entry and scale them entry by entry, and the zero vector is the matrix of all zeros. Every axiom holds. Second, functions. Take every function from the real line to the real line. The sum of 2 functions, f and g, is the function whose value at x is f of x plus g of x, and scaling f by c multiplies its output by c. The zero vector is the function that is 0 everywhere. This space is enormous, yet it obeys the same 8 rules. Third, infinite sequences, lists of numbers that go on forever. Add them term by term, scale them term by term. 3 completely different kinds of object. Grids of numbers, functions, endless lists, and all 3 run on identical algebra. That is the unifying power of the axioms. Now we zoom in. A subspace is a subset of a vector space that is itself a vector space, using the very same addition and scaling. The first good news is that you do not have to re-verify all 8 axioms. Most of them, commutativity, associativity, the distributive, and compatibility laws, are statements that hold for every element of the big space, so they automatically hold for the elements of any subset. Those come for free. What can actually fail is staying inside the subset. If you add 2 elements of W, you might land outside W. If you scale an element of W, you might leave W. That is the genuine danger with a subset. It can leak. So really there are only 2 things to worry about, that W is closed under both operations, and that W actually contains a zero vector to anchor it. That observation gives us a quick test coming up next. Here is the test, and it is short. A subset W of a vector space is a subspace exactly when 3 things hold. 1. W contains the zero vector. 2. W is closed under addition. Add any 2 vectors in W, and the result is still in W. 3. W is closed under scalar multiplication. Scale any vector in W by any number and you stay in W. That is all. If a subset passes these 3 checks, it is a full vector space in its own right. There is an even tighter way to say it. W is a subspace if it is non-empty and closed under linear combinations, meaning whenever U and V are in W, every combination A times U plus B times B is in W as well. That single condition folds addition and scaling together. A handy shortcut: if a subset fails to contain the 0 vector, you can reject it instantly without checking anything else. No 0, no subspace. One construction gives subspaces every single time: the span. The span of a collection of vectors is the set of all their linear combinations, every vector you can build by scaling them and adding the results. Here is the claim: the span is always a subspace of whatever space the vectors live in. Let's check the 3 conditions. It contains the 0 vector because taking all the coefficients to be 0 gives 0. It is closed under addition because adding 2 linear combinations of the same vectors just adds their coefficients, producing another linear combination. And it is closed under scaling because scaling a combination scales each coefficient, again giving a combination. All 3 pass, so the span is a subspace no matter which vectors you started with. This is the most reliable way to manufacture a subspace. Grab any vectors you like and take their span. Lines and planes through the origin are exactly the spans of 1 or 2 vectors. 2 subspaces come built into every vector space, free of charge. The first is the smallest possible, the set containing nothing but the 0 vector. Check it, it contains 0, adding 0 to 0 stays 0, and scaling 0 stays 0, so it passes the test. It is called the 0 subspace, or the trivial subspace, and it is the tiniest subspace there is. The second is the largest possible. The whole space V counts as a subspace of itself, since it is obviously a vector space living inside itself. So every space sits between these 2 bookends: the lone 0 vector at the bottom, the entire space at the top. Anything strictly in between, bigger than just 0 but smaller than the whole space, is called a proper non-trivial subspace. An ordinary 3-dimensional space, those in-between subspaces are exactly the lines and planes that pass through the origin, and those are the interesting ones we will study. Let's make subspaces visible in 3-dimensional space. Picture a flat plane tilted through the origin, shaded blue. 2 arrows, v1 and v2, lie inside it, leaving the origin, and their sum lies in the plane 2, drawn in gold. In fact, every linear combination of those 2 arrows stays in the plane, so the plane is closed under addition and scaling, and it contains the origin. It passes all 3 tests, it is a subspace. Now picture a second plane, parallel to the first but floating above it, shaded faint red. This plane does not pass through the origin, it misses the 0 vector entirely. By our quick shortcut, that alone disqualifies it: no 0 vector, no subspace. And you can see the closure fail too, because adding 2 vectors that end on the raised plane gives a vector that overshoots it. The lesson is sharp: subspaces must pass through the origin. A plane that floats free is not a subspace, no matter how flat it is. Here is the whole family of subspaces of 3-dimensional space, laid out as a ladder. At the very bottom sits a single point, the origin alone, the 0 subspace with no room to move at all. One step up are the lines through the origin. Take any non-zero vector and all its multiples, and you get a line, each one a 1-dimensional subspace. One step higher are the planes through the origin, the span of 2 independent vectors, each a 2-dimensional subspace. And at the very top is all of 3-dimensional space itself, the largest subspace. A gold chain threads up one path through the ladder, from the origin, up to a single line, up to a plane containing that line, up to the whole space. Every subspace of 3-dimensional space appears somewhere on this ladder, and they are sorted by how many independent directions they contain. That count is the dimension, and it is exactly the subject of the next episode. First worked example, the cleanest test there is, set in the plane. Part A, let W be the line of all points where y equals 2x, the line to the origin with slope 2. Does it contain the 0 vector? The origin is the point 0, 0, and indeed 0 equals 2 times 0, so yes. Is it closed? Add 2 points on the line, x1, 2x1, and x2, 2x2. The sum is x1 plus x2 and 2 times x1 plus x2, which is again of the form y equals 2x. So the sum stays on the line, and scaling works the same way. W is a subspace. Part B, now let U be the line y equals 2x plus 1, the same slope, but lifted up by 1. Does it contain the origin? Plug in 0, 0, is 0 equal to 2 times 0 plus 1? That says 0 equals 1, which is false. The line misses the origin, so it fails the very first check. U is not a subspace. A line is a subspace exactly when it passes through the origin. Second worked example, this time inside the space of all functions from the real line to the real line. Part A, let W be all functions whose value at 0 is 0. Is the 0 function in W? The 0 function sends every input to 0, so in particular its value at 0 is 0 is 0, yes. Is W closed? If f and g both vanish at 0, then their sum at 0 is 0 plus 0, still 0, and scaling f keeps its value at 0 equal to 0. So W is a subspace. The functions pinned to 0 at the origin form a perfectly good vector space. Part B, now let U be all functions whose value at 0 is 1. Is the 0 function in U? Its value at 0 is 0, not 1, so no. U fails immediately. And closure fails too. If f and g each equal 1 at 0, their sum equals 2 at 0, not 1, so adding two members of U lands outside UU is not a subspace. Pinning a value to 0 gives a subspace, pinning it to 1 does not. Third worked example, inside the space of 2x2 matrices. Let W be the symmetric matrices, the ones equal to their own transpose, so the off-diagonal entries match. A general one has A on the top left, D on the bottom right, and the same entry be in both off-diagonal slots. Is this a subspace? First, the 0 matrix is symmetric, since flipping all zeros gives all zeros, so the 0 vector is in W. Second, closure under addition. If A and B each equal their transpose, then the transpose of A plus B is the transpose of A plus the transpose of B, which is A plus B itself, so the sum is symmetric too. Third, scaling. The transpose of C times A is C times the transpose of A, which is C times A, still symmetric. All three checks pass, so the symmetric matrices form a subspace of the space of all 2x2 matrices. The same kind of argument shows the diagonal matrices form a subspace, and so do the matrices whose diagonal entries sum to 0. A short history, because abstraction this clean did not come easily. In 1844, Hermann Grassmann published a dense, visionary book that already treated vectors and linear combinations abstractly, in any number of dimensions, without leaning on pictures. He was so far ahead of his contemporaries that the work was nearly ignored in his lifetime. In 1888, Giuseppe Peano wrote down the axioms of a vector space in essentially the form we use today, the 8 rules, stated cleanly. In the early 20th century, David Hilbert and Stefan Banach pushed the idea into infinite dimensions, building spaces whose vectors are functions, and those spaces became the foundation of modern analysis. And in the 1920s, Emmy Noether and her circle made the axiomatic style the standard language of all of algebra. The thread is a steady climb in abstraction, from arrows to lists to any collection at all that obeys the rules. Let's recap. A vector space is any set with an addition and a scalar multiplication that obey 8 axioms: closure under both operations, commutativity, and associativity of addition, a 0 vector and negatives, the 2 distributive laws, compatibility of scalars, and scaling by 1 doing nothing. The definition says nothing about arrows, which is why so many things qualify: polynomials of bounded degree, matrices of a fixed shape, all functions on the real line, and infinite sequences are each a vector space. A subspace is a subset that is itself a vector space, and you test it with just 3 checks. It contains the 0 vector, and it is closed under addition and under scaling. The span of any set of vectors is always a subspace, the easiest way to build one, and every space comes with 2 automatic subspaces, the 0 subspace at the bottom and the whole space at the top. Next episode, we learn to count the true size of a space: linear independence, basis, and dimension. Today we set vectors free from arrows. A vector space is any collection of objects you can add and scale, as long as those 2 operations obey 8 axioms. Addition must be closed, commutative, and associative. There must be a 0 vector that changes nothing. Every vector must have a negative that cancels it. Scalar multiplication must be closed, distribute over both kinds of sums, be compatible with multiplying scalars, and leave a vector unchanged when you scale by 1. That is the whole definition, and it says nothing about arrows. So polynomials form a vector space, because you can add 2 polynomials and scale 1. Matrices of a fixed shape form a vector space. Functions form a vector space. Infinite sequences form 1. Each obeys the same 8 rules, so every theorem we prove applies to all of them at once. Then, subspaces. A subspace is a vector space sitting inside a bigger one. To check a subset, you need only 3 things. It contains the 0 vector, it is closed under addition, and it is closed under scalar multiplication. From that test, 2 facts follow. The span of any set of vectors is always a subspace, and every space has a smallest subspace, just the 0 vector alone, and a largest one, the whole space. Worked examples confirm which subsets pass and which fail. Historically, this abstraction is the work of Grassmann, Peano, and the early 20th century. Next episode, we count linear independence, basis, and dimension. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.